collision theory. Collision theory states that reactants of a chemical reaction must collide with one another with sufficient energy to react. So, chemical reaction, let's say NaCl. This chemical reaction means that to form NaCl, the Na plus and the Cl minus, they must collide with each other so that the chemical reaction can happen, and they should also have sufficient energy to react with each other. So energy is also needed. They must also collide in the correct orientation so that the chemical bonds are affected, allowing the chemical reaction to proceed. So they must also collide in the correct orientation. Okay, I'm sorry if you can't understand my handwriting. So that the chemical bonds are affected. So they are gonna get affected because of the correct orientation. They will need energy to make this bond happen. Okay? Allowing the chemical reaction to proceed. Many factors play a role in these collisions, including the concentration of reactants, temperature, nature of the reaction, and the catalyst is present. Catalyst is present. Nature of reactions, the temp, and the pH. Okay? Now, factors affecting the enzyme catalyzed reactions. Now we know when that pH, temperature, the nature, and the catalyst is present, all affect, and the concentration all affected, right? So there are various environmental factors that affect the enzyme catalyzed reaction. We must first remember that all chemical reactions are fundamentally caused by molecules colliding. So what are molecules colliding? Or the question could be, how are all the chemical reactions fundamentally caused? By molecules colliding, where all the chemical reactions are fundamentally caused. If the molecules that are colliding do so with high enough speed, and the molecules have the capability of reacting with each other, then there is a chance the reaction will occur. Enzymes cannot change those fundamentals. So you need high speed so they can collide and molecule collide in one. Now I'm going to talk about the temp. Imagine an enzyme and its substrate floating freely in a fluid environment. Both the enzyme and substrate are in motion, and the rate of motion is dependent on the temperature of the fluid. Rate of motion is dependent on the temp of fluid. Rate of motion depends on the temperature of the fluid. Fluids with higher temperature, the fluid has a higher temp. That means that they will have faster moving molecules. Higher temp, faster moving molecules, because it depends on the rate of reaction, depending on the temperature of the fluid. So, reactions that are dependent on the molecular collision, and as a rule, the faster molecules are moving, the more often they will collide. The more the molecules are moving, the more they will all collide with each other, just like how this X is making this collision. Okay? So, they collide with a greater energy. Reactions with or without enzymes will increase their reaction rates as the temperature increases, meaning the molecular motion increases. So without enzymes or with enzymes, if there's an increase in the reaction rate of temperature, the molecular motion increases. However, reactions that use enzymes don't have an upper limit. This limit is based on temperature at which an enzyme or the protein, because enzymes are made of proteins, begins to lose its three-dimensional shape. Now, enzymes are globular proteins. They are globular proteins. They have a three-dimensional shape. So, if the higher the temperature is there, the proteins in the enzyme, it can lose its intermolecular bonds, causing it to be broken. So, all these bonds that are in here, it then becomes like this. It's like that. This is known as denaturation. So, what is denaturation? It's actually, denaturation is more permanent, but sometimes it can be temporarily. This is very rarely. So denaturation will be permanent if the increase in temperature is such that it prevents a return to the native shape of the molecule. So denaturation is when the enzyme or the protein gets, the intermolecular bonds of the enzyme protein get broken, and that's denaturation, and that will be caused with the high temperature. But denaturation can also be caused of the pH. I'm now going to show you a graph of the temperature. So let me draw the x and the y axis. This is the y one and this is the x. This is the rates of enzyme, the catalyzed reaction, and this is the increase in temperature. So this is how it's going to be. Now, what does this symbolize? This is going to symbolize the enzyme starts to lose its shape, so the reaction rate begins to slow down. So enzyme lose shape, hence reaction will eventually slow down. This meaning there's an increase, this is an increase in the molecular collisions, and then this one right here, which is slowing down, the further increase in temperature leads to a rapid decline in the reaction rate as the enzyme continues to denature. Now I'm going to be talking about the pH. The active site of an enzyme typically includes a few amino acids. Some amino acids have areas that are charged either positively or negatively. Now I hope you guys know how amino acids look like. There is the N, H, NH, C, H, R, C, O. This is an amino acid. Now, amino acids are what includes or what is inside the enzyme, because enzymes are made of protein, and amino acids are the building blocks of protein. So amino acids, when they form together, they form a protein. So that will be an enzyme now. Well, it can try to dermatize, but it becomes an enzyme if it wants to. So they're trying to say that some amino acids have areas that are either positive or negatively charged. The charge areas of the substrate must match to the charge areas of the amino acid of the active site. So the charge area of the active site, it must match to the charge areas on the active site when the solution has become acidic. And you guys know acidic is that means there's a more concentration of H plus ions. Let's say over here, this is going to be 14. This is going to be the acidic, and right here is going to be basic. Okay, and it's going to be 7, which is going to be neutral. The more amino acids that have the H plus ion, that means it becomes more acidic. So the hydrogen ions can bond with the negative charge of an enzyme or substrate and prevent matching of the charges between the two. So the hydrogen bonds, they can bond with the negative. So these hydrogen, they can bond with the positive side of the enzyme, or it could be with the substrate. Okay, so it could be with this enzyme or it could be with the substrate. Now I hope you guys know this is not how the enzyme looks like. This is not the diagram, this is just the amino acid diagram, but this is not like the enzyme diagram. Okay, so please don't use that one because that will not be correct. Okay, so the hydrogen ions can bond with the negative charge of the enzyme or substrate and prevent matching of charges between the two. So why do you do that? To prevent the matching of the charges between the two. A similar scenario occurs when a solution has become too basic. That means if it's too basic, it becomes more OH negative ions. They bond with the positive charge of the substrate or enzyme. Once again, prevent the proper charge matching between the either two. Either of these scenarios will result in an enzyme becoming less efficient if the pH, let's say the pH changes, okay? If it changes, if it increases or decreases, the enzyme bonds will start to break, causing the enzyme to lose its shape and hence become denatured. So this is a good example, pH and the temp one, which also causes the denaturation. So there are one which cause denaturation. Whether or not the enzyme is permanently destroyed by denaturation is largely depending on whether covalent bonds, such as peptide bonds, are broken. To break this, How did I break the X? These peptide bonds over here, the peptide bond needs to be broken, hence can also form the denaturation. So let's take an example, DNA. DNA determines the order of amino acids and they have no way of reassembling properly if they become detached from each other. So DNA, I hope you guys remember, they determine the order of amino acid. Now, order of amino acid. Okay, now I'm going to explain to you the effects of pH rates on enzyme catalyst reaction. Just like how I draw the graph for the temp, this is either going to be for the pH. Now this is the rates of the enzyme. This is going to be the pH. This is going to be acidic, neutral, basic. Acidic is going to be like this, and then it's going to go like this. Okay, so over here we go see some special enzymes have an optimum pH that's acidic, so these enzymes will have the acidic one, and over here the neutral would be like the optimum pH 7, which is the body optimum pH. Okay, now I'm gonna go on the substrate concentration. Now this is a third factor of which can cause the denaturation. There's only 3 factors. If there is a constant amount of enzyme, as the concentration of substrate increases, the rates of reaction will increase as well. This is known as collision theory. Just as I explained, what is collision theory? Collision theory means that if there is a constant amount of enzyme, so this is the enzyme in the concentration of a substrate. Now, if the constant amount of enzyme it increases. Now, okay, wait. If the enzyme stayed like this and the substrate, little substrates, instead of being 4 substrate, it increases a lot. The substrate just concentration increases. The rate of reaction will increase as well. So these enzymes, they will all like go with these substrates. I hope you know that. So if the concentration of reactant molecules increases, if these concentration of reactant molecules increases, there are more molecules to react and collide with each other and the enzyme. There is a limit to this collision theory. However, because enzymes have a maximum rate at which they work, the only one active site they have, right? So if every enzyme molecule has an active site that is occupied, adding more substrate to the solution will not increase the reaction rate further. I'm now going to draw another graph. So this is going to be the x and y. So this is going to be the y and this is going to be x. It's going to go like this. So this is every enzyme molecule working as fast as possible. These are the enzyme working super fast. And this is the substrate increasing. Therefore, there's going to be more collision of enzyme colliding with substrate. Okay. So this is the rates of enzyme. And this is going to be the substrate concentration. And that's the whole graph basically. So the substrate, they're increasing and the enzyme molecule is working as fast as possible. And now the last part of the video is measuring enzyme catalyzed reactions. So if you measure the rates of enzyme controlled reaction, is similar to measuring the rate of any other reaction. It is possible to measure either the rate at which the substrate is used or the rate at which the product is produced. For example, in the investigation provided, the enzyme used is lactase. So if we use lactase, this is an enzyme that digests the lactose sugar into glucose and galactose. So lactose sugar, it's gonna go break it down into glucose and galactose, and that's what. So lactase, this is an enzyme. Okay, this breaks down into glucose and galactose. So the rate of the enzyme activity is measured by monitoring the rate at which the glucose is produced. That's the fourth factor. The amount of glucose produced is the rate of enzyme activity measured just by monitoring the glucose activity which is produced. And that's it for the SL portion. Thank you very much for watching.